Welcome to qnawire.
Over here we're asked to construct an energy level diagram of 2-pentene showing the relative order of the lowest 17 molecular orbitals at 38 degrees Celsius. So at 38 degrees Celsius we're told that we're going to have the trans isomer as being the main part of the main contributor to the structure of 2-pentene. So this means that we're going to have the model of a particle in a 3D box. In this case, the energies for the three-dimensional box would be equal to the value of h squared over 8 times m times the size of the box. This normally you're going to look at it as L squared times nx squared plus ny squared plus nz squared. Remembering that the values for nx and y and nz are going to go from 1 all the way to infinity, being all integer numbers. So 1, 2, 3, and so on. Okay, so with this we need to find out which are going to be the degeneracies, and for doing so, we're going to draw our orbital diagram from below all the way up. In this case, the first scenario is going to be having energy corresponding to the state 1, 1, 1. This would be equal to 3 times h squared over 8 times ma squared, which would be 3 times e0. Okay. Next up, we're going to have some degeneracies because the state corresponding to 211 is going to have the same energy as the state 121, and is going to have the same energy as the state 112, which would be equal to 6 times E0. Similarly to that, if we add now the state 221, 122, and 212, we're going to get 9 times the original energy. So this means that so far we have 3, 6, 7 orbitals, and we're going to have degeneracies on these points over here. Next up, we're going to have the energy corresponding to the state 311, which is the same as the energy 113, which is going to be same as the energy of 131. All of them is going to give us 11 times E0. Next up, we're going to have the energy for the 222 state, which is not going to be degenerate and would be 12 times the original energy, E0. And finally, we're going to have the state corresponding to 321, which is equal to the state of 312, which is the same as 231, which is going to be the same as 213, which is also going to be the same as 132, and which is going to be the same as 123. And all of these states are going to be equal to 14 times E0. Notice that if I take nx squared plus ny squared plus nz squared for all of these combinations, these are going to be equal to 14 on this scenario. So far, what we have is 1, 2, 3, 4. Sorry, let me put in red. 1. Let me put the degeneracy in red. We're going to have 1 state here, 3 here, 3 here, 3 here. So far we have 10, 11, and over here we have 1, 2, 3, 4, 5, 6 states. 6 states over here. So with this we have already 18 orbitals for this particle in a box model. So we can start with our diagram, since we have already our 17 states. So the lowest in energy, corresponding to 3 times E0, is going to be the 111 state. Next, we're going to have 3 degenerate states, which would be approximately this position, corresponding to the 211, 121, and 112 states. Next up, at approximately the same energy difference, we're going to have the state 221, 122, and 2, 1, 2. Next up, we're going to have another 3 degenerate orbitals corresponding to 3, 1, 1, 1, 1, 3, and 1, 1, 1, 3, 1, which is going to be a little bit closer in this case. The splitting is not that much. So now these 3 orbitals correspond to 3, 1, 1, 1, 3, 1, 1, 1, 3. Next up, we're going to have almost immediately after this the 2, 2, 2 state. And finally, we're going to have 6 degenerate orbitals a little bit above. 1, 2, 3, 4, 5, 6, corresponding to the state 1, 2, 3, 1, 3, 2, 3, 2, 1, 3, 1, 2, 2, 3, 1, and 2, 1, 3, which are all of the possible combinations. And with this, we have our energy diagram. Thank you very much, and have a good one.